All right. So hello, everybody. Welcome to our last seminar of the semester. Our last speaker is Dr. Breen. Just a quick reminder before I introduce her, we will not be taking any questions during the presentation. Keep your questions to the Q&A session, please. And I'm recording this talk for your information. Dr. Breen obtained her PhD in cognitive science from MIT in 2007 under the supervision of Ted Gibson. She's currently an associate professor of psychology at Mount Holyoke College in Massachusetts. Her research explores a variety of questions related to the perception and production of speech prosody, such as the factors determining which words are prominent and where word boundaries appear, and how speech production and comprehension rely on more general cognitive processes like attention, and how these processes are related to those underlying music production and comprehension. Dr. Breen's research has been generously funded by various agencies such as NSF, NIH, and James McDonald Foundation. Welcome, Mara. Can you please share your screen with us?
Yes. Okay, oops, I gotta make sure I'm sharing. Gotta make sure I'm sharing my sound as well. Right. And hopefully this will.
Perfect.
Okay.
Thank you. Okay, the screen is now yours.
Okay. And thank you all so much for being here. I guess it's a little bit of a silver lining of the current difficult situation that that we're doing more of these virtual talks, and so I can share this information, of course, not being able to travel to where you are. So thank you again for having me. So right. So as we said, the focus of my work really sits at the intersection of language and music and cognition. And so I think the overlaps in language and music really occupies this space of prosody, where both language and music, of course, use pitch information to organize information in time. Language and music both rely on phrasing. And then the focus of what I'm going to be talking about today is the metrical consistencies, similarities between language and music. And where I think these features make contact with cognition is in terms of attention. In other words, basically letting us know where we should direct our attention in time when we're listening in language and music. So let me start off by arguing that metric structure facilitates language processing. So as we know, cognitive processing resources are limited. And so in order for us to effectively understand, we have to selectively attend to moments in time. We know that we do this because words that occur in metrically strong positions are processed more quickly and more effectively. And what I'm going to argue for today is that adults actually signal metric structure during child-directed reading in ways that can train kids' attentional allocation mechanisms. And finally, that both listeners and readers represent metric structure during language processing. So that basically metric structure is pervasive through all of the ways that we use language. And so still by way of introduction, let me talk a little bit about how we study auditory attention with ERPs, because that's going to be the focus of a lot of what I'm talking about today. And so here's a beginning study. This is by Lisa Sanders and Laurie Astheimer at UMass Amherst. And in this study, there are two conditions. So one is the attend long condition. And so in this condition, participants' task is to respond to tones that occur 1500 milliseconds after a fixation. So they would first see a screen that tells them this is a attend long trial, then there's a fixation, and then a sound comes on. And so if that sound, if that tone occurs 1500 milliseconds after the fixation cross, the participant should press the button. But if instead it occurs 500 milliseconds after the fixation, they shouldn't press the button. And then the other condition is the attend short condition. And so now the participant's task is to only respond to tones that occur 500 milliseconds after fixation. So again, they get the name of the trial. If the sound occurs 500 milliseconds after fixation, they'll push the button. But if instead the sound occurs 1500 milliseconds after the fixation, they wouldn't press. So again, we've got the attend long condition and the attend short condition. And these letters represent individual trials. So the L's are trials in which the tone occurs at the predicted long duration, and then the S's are when the tone occurs after the unpredicted short duration. And in the attend short condition, we have those blue S's. Those represent the trials in which the sound occurs at the predicted short delay. And then the L's are when the tone occurs at the unpredicted long delay. So if we take the continuous EEG and we chop it up by these trials, where blue are the consistent trials and the pink are the inconsistent trials, and we average across those, we see a characteristic result, which is that on trials where the tone occurs at the predicted time, you get this larger negativity compared to trials where the tones occur at the unpredicted time. And so we call this early negativity happening around 100 milliseconds after the onset of the sound. We call that an N1. Okay, so that's a pretty basic task where you're just asking people to assess an individual time. But we can also use a similar sort of tool to identify attentional allocation in music processing. So this is a study by Aaron Fitzroy. He's my collaborator in a lot of this work, so you'll see his name coming up. And again, Lisa Sanders at UMass. And what they did in this study was they wrote these musical melodies in a particular time signature. So this one is in 3/4. And so all the participants do is they hear it, but the melody outlines this nice 3/4 time signature. And so in a 3/4, we know that beat 1 is metrically strong and beat 2 is metrically weak. So you have some notes in this melody that occur at these metrically strong times, and then you have other notes that occur at these metrically weak times. And so once again, if you average the ERPs elicited by notes in metrically strong versus metrically weak positions, we see once again this N1 effect, right? So the notes that occur on the beat 1s have a larger negativity in this early time window. And then we see a second effect that we're going to call the LMN, or the late metric negativity. And we're going to see that we see this effect on notes that occur at metrically strong times. All right, so again, looking at auditory attention allocation in music based on metric strength. And we can also use similar methods to look at auditory attentional allocation in speech. And for this, we take advantage of the fact that in English and in many other languages, word boundaries can be ambiguous. So for example, if I take a 4-syllable string like timer, derby, I can parse this in 2 different ways. So it could be timer, derby, where the second word is a disyllabic word, or I can parse this as tie, murder, be, and now the final word has 1 syllable, it's the word be. So we take these 4 syllables and we put them into 2 different metrical contexts that are designed to get people to hear one or the other parse of those syllables. So we have what we're going to call the disyllabic context, because it's designed to get people to hear the final word as disyllabic derby, or the monosyllabic context that's designed to get listeners to hear the final word as the monosyllabic be. So hopefully this sound will work, and I'll play these for you.
Banker, helpful, timer, derby.
Can you let me know if you could hear those? Can you nod? Yes, okay, great. So that's the disyllabic context. And hopefully, if I were to ask you what was the last word you heard, you would say derby. And then here's the monosyllabic context.
Banker, helpful, timer, derby.
Where here, if I were to ask you what's the last word you hear, I would predict that you would report the monosyllabic word be. Okay, and critically, across both of these final 3 syllables are acoustically identical. So all we've done is change things about the prior metric context in a way that we think is going to change how people perceive these last few syllables. So, so if we look at the results, first looking at the behavioral results. So what we did in this experiment was, so we're recording EEG while people are listening, and then at the end of each trial, we ask them to report what was the last word that they heard. And so what you can see here, we're plotting the % of disyllabic responses. And so you can see that even though on the majority of trials, people report hearing a disyllabic word, they're significantly more likely to do so when it's in that disyllabic metric context. And then the critical thing here is if we look at the onset of this final syllable, the word be, what we see is that in the context that was designed to get people to hear be as the final word, we see a larger N1 than when they hear that final syllable as the second syllable of the disyllabic word derby. So again, showing that we're seeing attentional allocation based on metric structure. So to summarize this intro section here, I would argue that regular metric structure allows listeners to predict the onsets of upcoming notes and syllables. And as indicated by these N1 effects, it shows us that listeners are directing temporal attention to the notes and syllables that occur at these metrically strong times, right? And that this facilitates the processing of those. And so what I'm going to show you is that, or what I'm going to argue is that children's books, and in particular adult productions of them, train attentional allocation mechanisms in ways that can facilitate language comprehension. All right, so the focus of these first two experiments is child-directed poetic speech. This is argued to be universal across languages, and I'm just going to show you one example that's specific to what I'm talking about here. Whoops.
Now, have no fear, said the cat. My tricks are not bad, said the cat in the hat. Why, we can have fun, lots of good fun, if you wish, with a game that I call Up with a Fish.
Okay, so this is former US First Lady Michelle Obama, and she's reading a book to a group of South African school children in 2015. This is important because the book that she is reading is actually a book that was published in 1957. It's called The Cat in the Hat by Dr. Seuss. It's extremely well known to kids raised in English-speaking households. And moreover, it has been translated into 12 different languages, including Turkish. And so Dr. Seuss, this author, is the most frequently read author among 0 to 3-year-olds in English-speaking countries, even 30 years after his death. And this particular book is the 8th most frequently mentioned book on top 5 favorite lists of 2-year-olds. So, and if you have any knowledge of this book, you'll know that Dr. Seuss texts are characterized by highly predictable metric and rhyming structure. And in particular, the story goes that this book was written in response to a publisher's request that Seuss write a book that would include all the words that 6-year-olds should know. And so he was given a list of 300 words that all English-speaking 6-year-olds should know, and he wrote the book with about 240 of them. And so what's also great about this is that most of the words in the book are monosyllabic and very simple and very high frequency. So we chose this, this excellent quintessential example of children's literature for our first experiment. So let me give you now the experiment outline of what I'm going to talk about for the rest of our time here. So in experiment 1, I'm going to show you some evidence that readers signal hierarchical metric structure in productions of The Cat in the Hat using variation in duration and intensity. And then in experiment 2, I'm going to show you some ERP results indicating that listeners create the same hierarchical metric structures even in the absence of explicit acoustic cues to that structure. And then finally, in the third experiment, I'm going to show you some other results from a separate ERP study where I'm arguing that readers are also generating hierarchic metric structure even when they're reading silently. All right, so in experiment 1, I'm arguing that adults impart metric structure during child-directed reading in a manner meant to train attentional allocation mechanisms. So if this is the case, then we should see that adult productions of child-directed poetic speech provide cues to metrically strong moments with prosody. So to do this, we first have to annotate the metric structure of this book. So here's one page of the book. I'm going to use this as my example throughout. So if we're reading this to my child, I would say, "Put me down," said the fish. "This is no fun at all. Put me down," said the fish. "I do not wish to fall." And I want to point out that Seuss routinely uses this feature of text emphasis that in most of his books, right? Using words in capitals to provide emphasis. So we can pull this apart and we can think about ways that we might annotate the metric structure. So if we kind of just start from basic poetics, we see that, that the Cat in the Hat is using an anapestic tetrameter structure. So an anapest is a metric foot comprised of 2 weak syllables and 1 strong syllable, anapest. So it is what it sounds like. And in each line of the book, there are 4 anapests. So that's how you get this anapestic tetrameter. Okay, but just talking about this in terms of anapestic tetrameter, it only gives us 2 levels of metric strength. We've got weak syllables and we've got strong syllables. And we think that there's a lot more structure to be found in the book. So, so we adopted 2 different ways of thinking about the metric structure of the book. And on the one hand, I'm going to call one of them linguistic meter and the other musical meter. And so first talking about the way that we thought about linguistic meter with the book, and this is based on the work of Fab and Halla, 2008. So they have this method of assigning linguistic metric structure in poetic context. And so they say, the first thing you do is you take all of the syllables and you assign them an asterisk, which we've done here. And we're going to call this metric level 1. And then the next thing that you do is you group those syllables into their metric feet and you promote the strong foot on whichever side that is up to the next level. And so I told you these are anapests, so short, short, long. And so if we group these with these parentheses, right, short, short, long, then this here is one of these metric groups. And so if we promote the right-hand side, then we get metric level 2. And then to keep going, because the ultimate goal is to go until you sort of run out of groupings that you can make, Fab and Halla say for the next group, you basically take each of these and you group them in 2 and you promote the right word node. So in this way, we get now at metric level 3, we have metric level 3 has strong syllables with fish and all and fish and fall. Now we continue to group, so now we'll group fish and all, and then we'll group fish and fall. That gets us to metric level 4. And then finally, if we group all and fall together and we promote the right word node, then we get metric level 5. So this gives us 5 levels of a linguistic metric structure. Okay, and then for musical meter, our intuitions were that when we are reading The Cat in the Hat, we're adopting a 6/8 metric structure. So the idea here is, right, assign all of these syllables to beats and to the tactus level in a musical meter. And we chose 6/8 because we think, first of all, that it's in 3, right, with the anapest, that gives us that idea. But to just have 3 beats, then again, you would only have 2 levels of metric strength, a strong and 2 weaks. And so we think there's more going on there, which is why we adopted a 6/8 structure, which allows us to think about 3 levels of a metric hierarchy. So we're going to argue that the first 2 syllables, put me, are in fact pickup notes or anacruses, and that beats 1 and 4, right? So this is a 6/8 structure. So 1, 2, 3, 4, 5, 6. So beats 1 and 4 are strong beats. They're accented. But in addition, we can also talk about primary and secondary accents in a 6/8 structure, so that we would say that beat 1 has a primary accent, beat 4 has a secondary accent, and then beats 2, 3, 5, and 6 are unaccented. Okay, so having done this, we now have, on the one hand, this linguistic metric annotation, where we're essentially making an argument that there are these 5 levels of linguistic structure, and we think that the acoustic features are going to bear out that relationship. And then we have this musical metric structure where we adopt the 6/8 time signature, and here we think we're going to see evidence of primary beats greater than secondary beats greater than the level of the tactus. Okay, so now that we've figured out all of these annotations, we collect some data. So we had 17 female speakers read the book out loud. 8 of them happened to read it to an audience of 4- and 5-year-olds in a classroom. 9 read it alone in the lab. We haven't found any differences between these groups, so I'm not going to talk about that anymore. We took these recordings and we force aligned them to the words in the book. We used the Prosody Lab aligner from McGill. And then, of course, we excluded some data points from analysis. In particular, we excluded multisyllabic words, and because they kind of complicate the issue of these acoustic features. And fortunately, there are very few of them, so only 49 out of 1,625 total words in the book. We excluded page final words because we didn't want to inflate any of the sentence final durations for the time that it took for people to turn the page, because they were reading it directly from the book. And then we also deleted repetitions, disfluencies, and words with durations that were greater than 3 standard deviations above or below the mean. So the two acoustic features that we're looking specifically at, first of all, our duration measure. And for what I'm going to talk about today, we're going to talk about duration as being the duration of the word that we're interested in, as well as following silence. So we've got duration, and on the other hand, we have intensity. And so we're looking at a standardized maximum word intensity, where we standardize intensity values across participants, because of course, you know, depending on where the microphone was when people were reading, we would have different baseline intensity differences across people. So again, the ultimate question here is, can we predict the duration and the intensity of individual words in the Cat in the Hat based on these metric models that I proposed to you, right? This linguistic metric model and this musical metric model. So the ultimate goal is to model the effects of metric strength separately for word duration and for word intensity. But of course, there's tons of other factors that are going to predict word duration and word intensity, right? We know this from a long history of study of language production. So to do this analysis, so we use linear mixed effects regression, and first we fit a control model where we included factors that have already been shown to predict word duration and intensity. And we talk about these in two ways. So we have intrinsic factors. So these are features of the individual words. And then we have contextual factors. So starting with intrinsic factors, of course, we have word length. So for example, words with more phonemes are going to be produced with longer durations than words with fewer phonemes. Word frequency matters. So words that are very high in frequency will be produced with shorter durations and lower intensity. And word class, so we looked at content words and function words separately, because content words are going to be longer and louder on average. And then we also looked at these contextual features. So first of all, the syntactic structure. So we did a syntactic parse of the book, and we kept track of basically the largest constituent that a word was completing, and predicted that with the greater size of the constituent, there would be an increase in duration. This is based on some prior work I did with Ted Gibson and Dwayne Watson. We looked at font emphasis. So this idea that Seuss uses capitalization as an index of emphasis. And so we predict that people will read those words with font emphasis as being louder and longer. And then we also took into account repetition, with this idea that when words are repeated, they get phonetically reduced. So shorter in duration and lower intensities. So we fit the control model with all of those parameters, and then we added the metric model on top of that. So we added metric level, and we did this in two different ways, and I'm going to show you the results, right? Because we did the linguistic metric model, we did the musical metric model, we did these separately. So we would add metric level from those models as both a fixed effect and then a random slope over participant, right? To take into account that different participants might be realizing aspects of metric strength differently. And then we used coding, we used contrast in the models so we could specifically test some of our predictions. So recall that for Linguistic Meter, we're proposing 5 levels of metric structure. So we used a backward difference coding measure, backwards difference coding for our contrast to test this idea that each iterative level of the metric hierarchy results in a subsequent increase in, say, the duration or the intensity. And with the musical meter, we contrasted beats against beat 4. So recall that beat 4 was what we suggested was the intermediate beat level, and so we're testing, is beat 1 greater than that, and are beats 2, 3, 5, and 6 less than that? And I know that that's a little confusing, and hopefully the results graphs will make some sense of that. So first, I'm going to show you the results of the model where we're predicting word duration using this linguistic metric model. Okay, and so here, right, this is level 1, level 2, level 3, level 4, level 5. And here are the coefficients of the model. And so I'll quickly say down here, we're showing the influence of those, of the factors that were in our control model, right? So features that have been previously shown to influence word duration, and they all do exactly what we think that they're gonna do. So that's great. And then here are the results from our metric model. And remember that I said that we encoded each level with backwards difference coding. So that means that this is the difference between level 2 and 1. This is the difference between 3 and 2, 4 and 3, 5 and 4. And so what you can see, all of these contrasts are significant. And when we look at the means, it's very clear that as we go up in this linguistic metric hierarchy, we are getting increasing duration of those words, right? So this is evidence that we're not just talking about 2 levels of a metric structure, right? If we were to think about this as an anapestic tetrameter, there's more going on here. Okay, and then if we look at intensity, and now we're going to use the musical metric model to look at intensity. So we're comparing beats 2, 3, 5, and 6 to beat 4. And what this coefficient is telling us is that beats 2, 3, 5, and 6, those are the ones in blue, are produced with lower intensities than beat 4, right? So this is the blues versus the green. And then beat 1 versus 4, this shows us, sorry, that was the blue versus the red. And now this one shows us the green versus the red, and those effects are both significant. So now if we look at the intensity means by musical meter, we see greatest intensity for beat 1, intermediate for beat 4, and then 2, 3, 5, and 6 are less. So basically what this is demonstrating to us is that linguistic meter is demonstrated or realized in variation in duration, whereas musical meter is realized preferentially in variation in intensity. Okay, and what's kind of nice about this is basically we see these effects similarly in musical phrasing as well. So just showing you here, so this is work done by Todd, 1985, looking at phrase closure and note durations. And so hopefully what you can see here is that with increasing closure in sort of a musical syntactic tree, you see longer durations of those final notes in a very similar way to what we see with duration variation in the Cat in the Hat. And similarly, Drake and Palmer, they looked at intensity variation in a 6/8 metric structure, and we see something very similar to what we see for our intensity effects, right? Greatest intensity on beat 1 in 6/8, intermediate on beat 4, and then 2, 3, 5, and 6 have less. So we're seeing that readers signal hierarchical metric structure in the Cat in the Hat with duration and intensity variation, and particular in ways that we also see in music production. Okay, so having shown that, now we're interested in to what extent do listeners actually recreate some of this metric structure when they're hearing a version of the Cat in the Hat that doesn't have any of these explicit acoustic cues in it. So again, my claim is that adults are imparting metric structure during child-directed reading in a manner meant to train attentional allocation mechanisms. So the hypothesis is that the metric structure in children's poetry will guide listener attention to metrically strong times, even in the absence of these explicit metric cues. So in experiment 2, I'm going to show you data from 27 participants who listened to synthesized productions of the Cat in the Hat while we recorded 64-channel EEG. Critically, these productions were devoid of suprasegmental prosody. So they were fully synthesized using a female voice in Ambrola. all of the syllables were produced with a flat pitch, and all the syllables were isochronous. So the syllables themselves were 300 milliseconds, and then there was a 125 millisecond ISI. So 425 millisecond IOI between syllables. And then we systematically controlled phoneme length within those syllables to make sure they fit, right? So, the voiced syllables would change their duration depending on the length of the syllable. Stops would always be the same. And you'll hear in a second what those sounded like. And so we had two conditions. We had one condition where the syllables were all in order, the book order, and then we had another where we put the syllables in a completely randomized order, and we counterbalanced presentation of these two, right, to control for the fact that that potentially having heard the version with the syllables in order might then sort of bleed over to how people heard the randomized version. And so again, we're recording continuous EEG, and then we average responses by beat in this 6/8 structure. So looking at what the materials look like, so down here on the bottom, again, we're looking at what the actual production looked like for one of our participants in experiment 1, right? Obviously lots of variability in duration and intensity. And then here's what it looks like for experiment 2, right? So every syllable is the same length, same intensity. And so now let's hear what that sounds like.
Put me down, said the fish. This is no fun at all. Put me down, said the fish. I do not wish to fall.
So you can imagine it's really fun to be in this experiment, but that's more fun than the randomized version, that's for sure. So I don't know if you had the feeling that you could kind of hear some of that structure, right? Did some of the syllables perhaps sound more intense to you? Did some of them sound a little bit longer? We'll see. Whoops. All right, so looking at our prediction, so now I'm taking that phrase, or the sort of that whole line, put me down, said the fish, this is no fun at all. And so we're looking again at the beats in that 6/8 structure. And so remember that the beat 1s are the strongest, and we showed this in our production results. Beat 4 have intermediate intensity, and then 2, 3, 5, and 6 have the least intensity. And then there's also, as I mentioned, there's this syntactic structure that we also want to keep in mind. And so here we're looking at how we defined these phrases, right? Put me down is a sentence, said the fish is another, and this is no fun at all, that's another. So our predictions here, if our listeners are creating, imagining, whatever, the hierarchical metric structure when they're listening, we're predicting the largest LMN, or this late metric negativity, to beat 1. We would be predicting an intermediate LMN to beat 4, right? Because that's second in metric strength. And we're predicting a closure positive shift to beat 4s. And so what we know from a lot of work on both linguistic phrasing and musical phrasing is that the ends of phrases often give rise to this positivity in the ERP waveform. But the thing is, it tends to be very late, so between 500 and 800 milliseconds. And if you recall, our syllables are all 425 milliseconds. So what we predicted here is if we are going to see a CPS in response to these phrase closures, which occur 69% of the time on these beat 4s, we're probably not going to see it on beat 4 itself. We're going to see it after beat 5, right? Because it's this very late response. And so we wouldn't catch it if we're just looking at those beat 4 responses. I hope that that makes sense. So now we're looking at the responses. So these are waveforms averaged over the entire head. And so you can see we've got all 6 beats here and where they correspond to the structure, the metrical structure in the phrase. And so what we see here, first of all, is this, as predicted, we get a late metric negativity to beats 1 and 4. And it's slightly larger for beat 1. Though statistically they're not different, but you see that the black and the green beats 1 and 4 are in fact more negative than the others at exactly this location, right, between about 300 and 500 milliseconds after the onset of the syllable. And in addition, we see this CPS, and like I said, it's very late, so it's actually showing up in response to beat 5, right? So it's sort of this overflow from an effect that we predict on beat 4. And then critically, when we look at the responses to the syllables in the random order, we see no effects at all. Okay, so what this then suggests to us is that listeners are able to create hierarchical metric structure when they're listening to the Cat in the Hat, even in the absence of these relevant acoustic cues, right? They're sort of imagining those aspects of the structure. So we think that that basically we're showing that neurocognitive mechanisms supporting metric grouping during music perception are also involved in metric grouping during speech perception. And since we've kind of we've done some more recent work where we're doing some source modeling based on the EEG results, and we're seeing that in fact these effects that we're seeing seem to be consistent with where these effects have been shown in some localization studies. So we're excited about where that's going. Okay, so now I've shown you production data where speakers are providing cues to metric structure. I've shown you some listening data demonstrating that listeners are creating metric structure even when they're not hearing it explicitly in the signal. And then in this third experiment, I'm gonna use ERPs again to argue that readers are also realizing hierarchical metric structure even when they're reading silently. So this is part of work that I'm doing on what we call implicit prosody. And I love this Twitter exchange as a great example of implicit prosody. So the initial tweet is, "Are you in love?" And then the retweet says, "I am so Yorkshire that I read this as someone asking if you're at home." And so hopefully that makes you reanalyze this. So it's not, "Are you in love?" It's, "Are you in love?" And if you can do that, if you can do that reorganization while you're reading it silently, that suggests that you are creating this implicit prosodic structure, right? Where you're putting a boundary in here. I don't know, maybe none of you are Yorkshire English speakers, and so this isn't relevant to you, but I think it's a fun example. Okay, so in experiment 3, we are predicting that readers will generate implicit metric structure while reading silently in ways that facilitate text interpretation. So if this is the case, then the hypothesis is that ERPs will reveal different patterns to words depending on both metric structure and consistency with the context. So let me explain a little bit more what I mean by that. So it's challenging to investigate implicit metric processing, right? Basically, we're trying to assess what are people imagining as they're reading silently. So here's the logic that we use for this experiment. So we think that if readers are representing metric structure during silent reading, they should have processing difficulty when the stress pattern of a target word doesn't match the predicted metric structure of the context. And English offers us a great way of assessing this because we have these words that we call stress alternating noun verb homographs. So these are words that when they have strong weak stress pattern, they are nouns like address, permit, present. And when they have a weak strong stress pattern, they are verbs like address, permit, present. And so the idea here is we can take these words and we can embed them in highly constraining metric contexts and look at cases where the word doesn't match what you're predicting. And so the context that we're going to use are these, again, poetry, limericks. And so if you're not familiar with limericks, here's an example. There once was an old man from Esser whose knowledge grew lesser and lesser. It at last grew so small, he knew nothing at all, and now he's a college professor. Ha ha ha. Okay, I'm not seeing any laughs. All right, so the thing about limericks is, again, they're very tightly constrained in their metric structure, alternating weak and strong syllables, actually not so different from the Cat in the Hat. Weak, strong, weak, weak, strong. And so they present this great context in which we can investigate implicit prosodic processing. So what we did was we wrote the first 2 lines of limericks, and we put these stress alternating noun verb homographs as the last word in these couplets. And I'm going to show you that this final word was either consistent or inconsistent with what you would predict based on the previous stress pattern. So first example, there once was a penniless peasant who couldn't afford a nice present. So the target word that you're predicting based on the context is strong, weak, and the stress pattern of the word is the noun form, strong, weak, present. So we call this the strong, weak, consistent condition. Next, we have there once was a clever young gent who gave to his girl a present. So now the context is getting you to predict a weak, strong word, but the word you get is strong, weak. So we're going to call this strong, weak, consistent, right? Because the target has a strong, weak pattern, but it's inconsistent with the context. Next, there once was a clever young gent who had a nice talk to present. So here, the target word has a weak, strong stress, and it's consistent with the context where you're predicting weak, strong. So that's the weak, strong, consistent case. And then finally, there once was a penniless peasant who went to his master to present. So now, predicting strong, weak, but you get a weak, strong target. So this is the weak, strong, inconsistent, right? So we're fully crossing both the stress pattern of the target word and the prediction of the stress pattern from the context. And so here's just another way of looking at those 4 different conditions. And so you can see that we have these 2 marked cases, right? Where the stress pattern of the target word doesn't match what's being predicted. Okay, and so we have some prior work from the ERP literature that might inform the predictions that we would have here. And I'm just going to show you one example. So this is Kryakova and Mani 2016. And so they had participants read word lists in German. I'm not going to try to produce them, but they were, so here are 3 words with strong, weak stress, and the target has strong, weak stress. Then here's 3 words with weak, strong stress. The target is strong, weak. Then you have all 4 words have weak, strong stress, and then you have 3 strong, weak, followed by a weak, strong, right? So similar to us, you've got the crossing of the target stress pattern and the stress pattern predicted by the context. And so what we see in their results is that when you have an inconsistent strong, weak word, you get this early negativity. When the target is strong, weak, and it's inconsistent with the context, you get this early negativity. But whereas if the target is weak, strong, and it's inconsistent, then you actually get a positivity relative to a consistent weak, strong target. So, if readers are doing the same thing in our study, we should predict these same sorts of results. All right, so for this experiment, we collected continuous EEG from 19 participants while they silently read these rhyming couplets. This was a within subjects 2x2 design. So we're crossing again the target stress pattern. Is it strong, weak, or weak, strong? As well as consistency with the metric context, right? Whether that target is consistent or inconsistent with the context. We had 320 trials, 40 experimental items by 4 conditions, and these were based on a study I did with Chuck Clifton now a bunch of years ago. And so every participant saw every version of each of the target couplets. And in addition, we had 160 totally metrically consistent fillers that didn't have any stress alternating noun verb homographs. And just to see kind of how all these worked, right? So they read 320 couplets total, 160 were metrically consistent fillers, and then 160 experimental stimuli, of which 80 were consistent and 80 were inconsistent. So critically here, only 25% of the couplets that they read had this metric mismatch. And this is important because, of course, we want them to continue to be sort of surprised by this, right? Have it continue to be unexpected. And so because we're doing this as an ERP study, we needed to control presentation. And so this is how we did it. So each Each one of those couplets was divided into 6 segments. Each segment consisted of at least only one stressed syllable, and then 1 to 3 unstressed syllables. So there once was an old man named Kermit who hunted without any permit. And critically, the target word was always presented alone on the screen for 2000 milliseconds at the end. All right, so turning to the results, again, here are those 4 conditions. And so here on the left, we're looking at cases where the target is a strong, weak target. So that's these 2 here. And what we can see is, kind of surprisingly, we see this early, kind of looks like an N1 effect to an unpredicted strong, weak target. We're not entirely sure what to make of this because we don't see a version of this in the literature, particularly in cases where you're looking at implicit sound, right? So it might be something that we would expect if people were really hearing these out loud, right? Because I showed you earlier that sounds are driving this early N1, but we were kind of surprised to see it here. But if you recall those results I showed you from German, we see that same effect where a strong, weak target a strong, weak target that's inconsistent with the metric context gives us this negativity relative to a strong, weak target that's consistent. But then we see the opposite effect for the weak, strong targets, where now the weak, strong, consistent is here, but the weak, strong, inconsistent now gives us a positivity relative to the consistent. And so you can see that that early N1 was mostly left lateralized, but these later effects we see all over the head. So summarizing these effects, we see that these inconsistent, strong, weak targets elicit an early negativity and a later negativity relative to consistent, strong, weak targets. And on the other hand, the inconsistent, weak, strong targets elicit a later positivity relative to the consistent, weak, strong targets. And these results are consistent with prior studies of metric prediction in language, both in silent cases and in overt listening. So what we think these results demonstrate is that readers are representing implicit metric representations during silent reading that are similar to explicit metric representations. And moreover, that the neurocognitive mechanisms that support metric grouping during overt listening are also involved in metric grouping during silent reading. So in summary, in the first experiment, I showed that readers signal hierarchical metric structure in this children's book, The Cat in the Hat, with consistent duration and intensity variation. And then in experiments 2 and 3, showing that in addition, listeners and even readers also represent metric structure, even in the absence of explicit acoustic cues. So I think that in total, this suggests that adults are providing cues to metric structure during child-directed reading in ways that can train attentional allocation mechanisms and in addition support reading acquisition and comprehension. So we're continuing this sequence of studies with future work. We are assessing data now where we're looking at the relationship between explicit productions and silent reading for the same set of materials. We're looking at the longitudinal development of implicit prosody and its effect on reading ability. So looking at kids along a trajectory to see how their productions of The Cat in the Hat correspond to standardized assessments of reading ability. And then finally exploring explicit and implicit metric processing across languages. So we have a study right now. I have a student who's collecting productions of El Gato Ensombrerado, which is The Cat in the Hat in Spanish. And I have another student who's working on a Mandarin version of the book. And maybe someone's interested in collaborating on Turkish. So I want to thank my students, in particular, my postdoc and collaborator, Erin Fitzroy, and then my Mount Holyoke students who have been intimately involved in all of this work, and the James S. McDonald Foundation for funding support. So, and thank you to all of you.
Well, thank you very much, Mara. I'm going to applaud you on behalf of everybody.
Thank you.
All right, so we will take the questions now. Junior researchers first, students, junior researchers. If you have any questions, you can either type in the chat box. I mean, just say something like, I have a question and I'll let you speak. Or you can raise hand. the researchers?
Are you asking everybody for questions or just as, I'm not clear, I'm sorry.
First, we are going to be taking questions from students, and
Okay, right, okay, good.
but I think they don't have any. So let's start with, okay, so there's Elif Kaplan. Elif, can you unmute yourself, please?
Well, could we go back to
Oh, wait, hold on. I think a student had a question first.
Elif?
Is that right?
Yes.
Yeah.
Yeah, hi. Thank you for the really nice talk. It was really interesting. I wanted to ask you a question about the second experiment you conducted, where you took out the acoustic cues and you found the metrical structure's representation. Yep. What do you think would happen if you were to present mismatching metrical cues, like where you deliberately manipulate the prosodic boundaries that mismatch the expectations of the participants? What would be your expectation to observe?
Yeah, I think it'd be really confusing. But so in terms of the ERPs, I would predict, I mean, we generally see CPSs to any prosodic boundary, so we would probably see those. I suspect they'd be larger if they were inappropriate in that case, and I think it would really kind of mess with people's perception of what they were reading, for sure. Yeah, what do you think?
I don't know, like if the acoustic cue actually would generate the expectation of what the prosodic boundary would be, regardless of the implicit metrical structure, you might observe something similar to that of the data that you found.
So right, it would be an interesting question to see to what extent are people able to, right, so if I'm arguing that these results are showing that people are actually creating that that metric structure and that phrasing structure, even in the absence of those cues, I guess it would be interesting to see, would you show effects of both, right? Both sort of that predicted metric structure as well as responses to some explicit acoustic cues. But I could imagine you could potentially have a trade-off, right? Because if those sort of inappropriate cues that you are putting in are gonna sort of confound expectations, and so maybe you wouldn't be able to kind of keep that correct metric structure that you are kind of creating in the face of that conflicting information, right?
Mm-hmm. Thank you.
Yeah, thanks.
Okay, thanks, Elif. Isra Hocam, would you like to go ahead and ask your question?
Yeah, thanks, Mara, for this wonderful talk. The third experiment, really, I was thinking of whether one could come up with a condition where this implicit metrical processing could somehow be at least, subdued, let's say with a dual task setup, and where they would do a second task during, the reading. And I also thought of, but I'm not familiar with that literature. While we were discussing short-term memory, the phonological loop and all that stuff in human memory with my students, I kind of gave an example of how sometimes I read things when I have to read really fast without moving anything in my larynx. It's like as if my eyes read it. I don't have the subvocal thing. So I wondered whether one could maybe look at individual differences, participants who can read without, doing the subvocal part, and then see whether you'd still find these ERPs, or maybe for that group, you wouldn't find it, which would also be a nice additional piece of, confirmation for what's happening mostly if one reads things implicitly.
Right.
Do you have any ideas on that?
Yeah, okay, great question. So the first one where you said, what if they're reading these limericks with some other task? And in fact, Dan Grodner at Swarthmore, he's sort of an academic brother of mine. He actually has a student who's been working on this. And so their initial results suggested that in fact, so we had initially done this as an eye tracking study, Chuck Clifton and I, about 10 years ago, and we showed, right, like longer go past times on the target when it didn't match with the context. And basically, Dan Grodner and his students showed a reduced cost of this metric violation when the participants were also doing this subvocalization task, right? So yeah, so you're right about that. And then yes, individual differences are exactly what we are trying to do now. And there is some evidence, right, that individual differences in the way that people produce different aspects of prosody contributes to the way that they perceive them. So work by Sherry Spear, and I can't remember, is it Spear and Konopka? I can get the reference for you. So they recorded people reading these paragraphs that had contrastive focus, and they showed that only for the people who realized contrastive focus with, you know, a particular prosodic feature were then demonstrated longer reading times on focused things when they read them silently. So right, that was some evidence that the way that we produce different prosodic features out loud seems to also correlate with the way that we do it silently. And so the way that we're trying to assess this right now is we've spent the last couple of years collecting this huge set of data from participants where they do some silent reading on the eye tracker, they do some reading out loud. Some of that material is identical, some is different across those. And in addition, we're collecting a whole bunch of standardized assessments of digit span, of vocabulary, rapid automatized naming, author recognition test, but basically trying to, all of the sort of standardized assessments that have been shown to predict differences in prosody we want to see, well, do they predict the same variance in both overt productions and in silent reading? So we'll be working on analysis of that this summer.
Okay, thank you.
Yeah, thank you.
Okay, so Professor Keither, would you like to ask your question?
Oh, yes. The limerick meter, I think that, good. What meter is that? The reason
I'm not sure.
You see, that's
what do you think?
Well, what I think is that this is actually a complicated problem because Robert Frost once observed that in English there were really two kinds of meter, loose and strong iambic.
Okay.
And basically what he meant by that was that in strong iambic, if you take a look at the first line there, strong iambic would simply be repetition of the metrical position WS 5 times.
Yep.
So the two W's between the first and the second S are then problematic. Well, that's what was weak iambic. Weak iambic, strong iambic said that there had to be a one-to-one mapping between syllables and metrical positions.
Okay.
Weak iambic said that there could either be one or two. So the metric here could in fact be iambic. And in fact, that's what I think it is. Now the question there becomes, for me then, what happens when you have things like present versus present? And I'd have to, can you show me that again? Can you show me a slide where you have that meter? Or maybe there wasn't.
This one here?
No, I'd like to see the metrical pattern. I'd like, yes, let's see, show me one where you get present and present.
These here?
Yeah, okay, so you have gent there and present, and that's okay, but you have gent and present. You see, the problem is that one of those lines is unmetrical.
Yeah.
And that's what and so what I'm thinking here is sort of intuitively because there's a lot of factors going on. But what I'm thinking is, I like the idea very much that a reader is projecting, that is to say, hypothesizing a metrical pattern based on the data of the lines. That's basically what you're saying. And now the question is, which one is he or she projecting? And that isn't clear to me from the talk. And so I guess what I'm really saying is, can I take a look at your slides sometime?
Yeah, absolutely. Is this slide more helpful? So here I'm suggesting what the predicted stress pattern would be.
Well, you see, yes, let me see.
So
I think he gave to his girl a present is unmetrical. That line would be unmetrical. Because you would have a strong position pres in a weak, corresponding to a weak position in the line.
Yes, and that's right. That was exactly the manipulation, right? But so what we're saying is we should see effects of that if people are actually creating this metric structure when they're reading silently, right? That yeah, this star here, we're saying like this was wrong, as is this one, but this one's now wrong for a different reason, which is that you're predicting a strong syllable and you get a weak, right? Whereas here you're predicting a weak syllable and you get a strong.
So okay, so that's what I'd like to take I want to double check my thinking about this, but essentially what you're saying is that the reader projects a metrical pattern, then performs a scansion and reacts to the inconsistent one by saying it doesn't scan.
Yeah, if you know, that's one way to, so here are those results, right?
Well, what you'd be saying is that the decision it doesn't scan shows up as some sort of calculation here. What's this red line?
Yeah,
and
this one here.
Red line represents what, negativity?
Yes, so this is a negative negative deflection relative to.
What exactly does that mean, negative? What's negative?
What? Oh, wow. So in some ways it doesn't mean much, right? Like we can't necessarily connect it directly to brain processing, but you know, if you're familiar with like the N400, it's possible that this is a version of that, right? Where basically you get some unmet prediction. That's one interpretation of what the N400 is, right? Where we actually see an N400, we see like a characteristic kind of multiphasic response in the ERP to any word onset, and the N400 we see to every word, but just the amplitude of that N400 is larger to the extent that the word that we're seeing doesn't match with predictions. Generally, we think about them as semantic predictions. So I don't tend to call this an N400 here because I don't think it meets those requirements. And in fact, a similar type of deflection like this has been shown to occur over and above an N400. So in cases where you have people listen to words that both mismatch in terms of the semantics and mismatch in terms of the metric structure, you get additional effects of both of those. Does that help?
No, but that's not your fault. I'm not familiar with this kind of terminology, so
okay.
I don't really know what I see on the left there amplitude, and what you're saying is that amplitude is higher. And how is an amplitude is measured by a reaction, a reader's reaction?
So so all of these, right, are averages over these different 4 classes of trials, right? And each one of these lines for this trial, like all 4 of these lines are in response to exactly the same word, right? And of course, then there's 60 of them there's 40 of them in the whole experiment, right? There's 40 separate words. And then each one of these lines is the average of 40 possible words. And then, of course, for not every participant do we get all 40 trials. But the idea here is we're comparing, right? So they're seeing the exact same orthographical content on every one of these trials, but the fact that those give rise to different brain responses depending on the context allows us to interpret these differences as due to this conflict between what you are predicting and what you actually perceive.
Well, that's interesting. I wonder how this would work on more sophisticated metrics. Like, for example, there's this line from Keats, how many bards gild the lapses of time, which appears in a perfectly iambic.
Oh, yeah.
But the line is unmetrical. And what would you predict?
Well, there's a few things that I think are going to go into that. So first of all, it's going to depend on how consistent everything was prior to that moment, right? Because I think in...
Oh, you mean in the line, how consistent everything is in the line?
Yeah, or even in stanzas, you know, preceding stanzas, right? Because I think, you know, we are very good at cueing into the statistics of whatever we're reading, right? And so part of the reason why we chose limericks is because when people know limericks, they know how tight the constraint is on what the metric pattern has to be. And so I think, but if you're talking about someone like Keats, then perhaps there's not that same understanding that it's always going to be very strict, right? The second challenge is, in order to do an ERP study like this, we need multiple trials with the same features, right? So here we used basically all of the stress alternating noun verb homographs that we could possibly use, and we came up with 40 of them, right, that undergrads would actually know. And so if you want to test that Keats example, it's hard to do. You can't do it with ERPs with just a single trial. It depends on being able to average across lots of trials, because any individual trial, right, there's so much going on in our brains while we're like listening to poetry or reading poetry, that we need to average out that noise with a lot of iterations. And so in that case, you'd have to find sort of lots of different poems that have exactly that same sort of conflict with predictions, right?
Well, the point of the line is that the line is unmetrical, and it's in a sonnet, and it's the first line.
Okay.
And it's a joke, because the line begins, how many bards gild the lapses of time? And lapse is unmetrical. It corresponds to a W position when it should correspond to an S position. So what Keats is doing is he's making a metrical pun.
Yep,
See,
I get it.
Okay, so you have to know that in order to get the joke.
Right.
But that shows that you have to have the meter in your head, or else you can't get the joke.
Yeah. Yeah. So so according to these results, then we would, you said it's a weak when you're predicting a strong, right? I think.
Yes.
So then I would predict something like this. But again, we wouldn't be able to look at just a single trial to see that result, right?
I see.
But you know, you could probably, maybe a simpler way to test it would be with an eye tracking study. So we would also expect that that these mismatches would result in inflated reading times, that you have to take longer to figure out what it is that you're looking at. But again, you'd have to find sort of multiple case studies, right, of that sort of thing happening, of predicting a strong syllable and then getting a weak one. And then the joke part, you know, that's a whole other level.
I think, I don't want to take up too much. I wonder if we could talk some other time about this.
Sure, I'd be very happy to do that. Yeah.
That would be great, because I feel as if I'm being hoggish here. So but thank you very much for a really interesting talk. And,
Thank you. Thank
I
you.
like very much about it is that it essentially shows that people actually are making hypotheses about a metrical line that
Yes.
internally, even if they're not hearing anything, and that's very important.
Exactly. Yeah, thank you.
All right, thanks. Any other questions? Anyone else? No one else? Well, okay. Thanks, everybody. Thank you very much, Mara, for your time.
Thank you so very much for having me. It was such a pleasure.
Of course.
Same here.
Well, thanks, everybody. We made it. We made it to the end of the semester. Well, stay safe and healthy, everybody, and take care. Bye-bye.
Bye.